right, thanks very much, everyone. Thank you for taking the time out of your evenings to come hear about muons and muon collider. So really, I want to tell you a particle physics story tonight. It's a story that stretches almost a century, so it covers a lot of ground. It also goes from the shortest accessible distances to the longest visible cosmological distances. And the best of all, at least the favorite for me, is it's also an underdog story. So hopefully, through the course of the evening, I can tell you a little bit about each part of that tale. I want to start with just a little bit of a preface. I always do this whenever I'm talking about sort of stories in particle physics. There's really only two things that you need to know to understand, I think, all of particle physics, apart from the psychology of particle physicists. Particle physics is really the combination of the theory of special relativity, which we got from Einstein, and the theory of quantum mechanics, which of course we got from Einstein and many others around the turn of the 20th century. And each one of those, special relativity and quantum mechanics, gives us a key insight that really drives the enterprise of particle physics. The first one comes from special relativity, and basically it means that particle physics is actually alchemy, right? Alchemy is the age-old idea that we can transmute elements into gold. Of course, we've learned that that's complicated, but particle physics actually does something that's very similar to that. The basic idea, first I should say, something you'll know you're around particle physicists when they start drawing diagrams like this. This is what we call a Feynman diagram. It's a space-time representation of how particles fly through space and interact with each other. And for example, what this picture shows you, you can imagine this is a direction in space, this is a direction in time. Each one of these lines is a particle, in this case a charged particle, two different types, and they interact with each other, they feel each other's charge by exchanging another particle, a force carrier, in particular the photon, which carries, transmits the force of electromagnetism. And so what this picture is just showing you is that two charged particles, if they have like charge, they'll see each other's charge and they'll bounce off in opposite directions. What special relativity tells us, right, is you can sort of exchange space and time. And so if this diagram exists, you should be able to turn it on its side and get this diagram. And what this diagram is telling you is if you have a charged particle and its antiparticle, you can smash them together, and through this force carrier, you can actually make something completely different. And the only price that you pay for doing this is that you have to smash these particles together with enough energy to make the rest masses of those new particles. And so basically by smashing things together with enough energy, you can turn things that you know into things that you didn't know. And so this is the sort of sense in which particle physics is alchemy, and it's really a gift to us of special relativity. The other thing that's, I think, important in thinking about particle physics comes from quantum mechanics. So, of course, in quantum mechanics, as you probably know, there's a sense in which things are both particles and waves, and the distinction is actually not really well characterized. But actually, the other important thing we learn from quantum mechanics is once you can create and destroy particles, in other words, once the number of particles you have can change, the way you describe the whole system should shift a little bit. And instead of talking about particles as the fundamental things themselves, what we do is we imagine that for every sort of fundamental object in the universe, it corresponds to what we call a field. That's something that lives everywhere in space and time. And if we wiggle the field, if we excite it, then we make particles. So the particles that we see are actually excitations of something more fundamental that we call a field. A good analogy is just to think about a lake. Lake is full of water. Okay, the water is like the field. And if you drop a rock in, all right, you make ripples. Those waves propagate across the surface of the lake. Those are like the particles. They're the excitations of the water in the lake. And that basic idea is in operation everywhere in the universe. And sometimes I'll pass back and forth between these ideas. The field is the thing itself that lives everywhere, and particles is the excitations that we get by shaking it. Okay. So now I told you this is a story that would span more than 90 years. And so what I want you to do now is cast your mind back to 1932. And we can ask, what was it like to be a particle physicist in 1932? And in particular, you can ask the question of what did particle physicists think the universe was made of in 1932? And the answer is they thought it was made of about four things. They thought it was made of protons and neutrons, which together made up nuclei, the important heavy parts of atoms. The electrons, which are the other things that showed up in atoms. And the photon, which was the thing that allowed the charges of these particles to talk to each other. And loosely speaking, the reason that we sort of knew that this was the particle content of the universe at the time was this is the stuff that everything is made of. You and me and the room we're in, it's all made of these things. And so once you're able to sort of pull them apart and look at them, it becomes clear that the universe is made out of this stuff. Of course, we know now the universe is a much more rich and complicated thing, and the reason this diagram looks peculiar is later in the talk we'll fill out all the rest of it. So the question is, how did we go from this picture to the picture that we now have in the modern day? And the answer is we actually started even 20 years before that, before 1932. by sending balloons up to make measurements very high in the atmosphere. So this is a picture of Victor Hess. What Victor Hess did is he actually took a very interesting scientific tool of the early 20th century called the electroscope. What this is it's a metal plate that's then connected to a wire into a little vacuum chamber, and this is a piece of gold foil that's just draped over the end of the wire. And what happens is if you start adding charge, or electrons, to the top of this, they'll come down, distribute themselves along this whole system, they'll end up in the foil, and in the foil they'll repel each other, and so they'll push the two ends of the foil apart. Okay. So if you charge this up, the two ends of the foil will come apart. And something that people had learned in the early 20th century is if you put a radioactive source next to this electroscope, eventually, actually, the electroscope would discharge. In other words, the pieces of foil would flop back down onto each other. And the reason for that was that you either knocking electrons off the plate or you actually absorbing something else that was canceling the charge. Okay. So what Victor Hess did is he said, well, let me take this and now let me take it up into the atmosphere. So the idea was these radioactive sources, they're here on the Earth. As I take them up in the atmosphere, that effect should go away, right? The leaves on the electroscope should stay far apart. And he found the opposite happened. The further up you went in the balloon, the more quickly the electroscope relaxed. And so after a lot of thinking, right, he understood something profound was happening. Radiation actually must be coming from space, because the further up you go in the atmosphere, the more quickly this happened. And it must be radiation from space that was actually discharging the electroscope. And indeed, this led to the discovery of cosmic rays. Cosmic rays are particles that are coming from the sun, from within the solar system, from outside the solar system, sometimes even outside the galaxy. Mostly they're ordinary stuff, things like protons and neutrons. But when they smash into the atmosphere, of course, they create a shower of energetic particles. They undergo this process of alchemy in particle physics. And they convert all their energy into other things. And crucially, they convert their energy not just into the stuff we're made of, but other things that we had no reason to know were there, except that the energy from these cosmic rays was converted into making them. And so that led to a whole period of sort of epic discovery of new particles that were not the things we were made of. And the way they did it was by building increasingly sophisticated ways of actually seeing what the particles were being produced by these cosmic ray showers. In particular, where our story really picks up is with Carl Anderson and Seth Niedermeyer, who built more sophisticated detectors known as cloud chambers. These are very careful chambers where they almost want to make clouds, and when a charged particle shoots through them, actually that's enough to make a little cloud in the trail of the particle, much like jets make contrails as they fly through the atmosphere. And if you put that whole thing in a magnetic field, the charged particles, as they leave their trails, they'll bend one way or the other. The amount by which they bend and the direction they bend tells you about their mass and their charge. And so they were able to make measurements of these cosmic rays and learn that a lot of them were indeed things that we already knew about. But then they discovered, in the late 1930s, they discovered there were some things that we didn't know about, because they saw evidence for particles whose masses were greater than that of the electron, but less than that of the proton, whose charges were quantized in the same units as the electron charge and the proton charge, but were neither one nor the other. And this was a sign that there was something new that was related to the particles we knew, but distinct on its own. And so this indeed was the discovery of the first thing that was in some sense not a thing that we're made of. This was the discovery of the muon. So by 1937, we were able to add to this picture of things that we were made of a new particle, which was in many ways like the electron, had the same charge. It was about 200 times heavier. And crucially, the reason we're not made of muons is it's unstable. It decays in about 2.2 microseconds. So we required to have it be made high in the atmosphere and make it all the way down to Earth to discover it and know its properties. But this was, a paradigm shift, because up until that point, everything else that we knew about was stuff we were made of. It played a role, right? It was responsible for life and everything, the universe and everything. Whereas the muon, nobody asked for that. It didn't do anything. And so famously, I.I. Rabi was purported on the discovery of the muon to have said, well, who ordered that? Subsequently, then, physicists said, well, great, cosmic rays are a way that we can discover, we use this alchemical way of creating new things out of the things we know. We can ask, is there even more? But we need to have more control over the system. We can't just count on random things hitting the atmosphere and trying to determine what's happening in detectors. So starting in the 1930s, a series of physicists, including E.O. Lawrence, came up with ways of doing this in the lab, accelerating particles to higher and higher energies, first just smashing them into other objects, or sometimes smashing beams of particles into each other, and converting that energy again into new things which you could discover carefully in the laboratory. So this is an image of one of the first cyclotrons, which is just a way of accelerating charged particles in a ring until you smash it into an object and see what you get. In fact, this started in the 1930s, a whole succession of developments of more and more energetic particle accelerators designed to do basically the same thing that cosmic rays do, but at higher energies and in very controlled ways. So this is a plot, this is what's known as a Livingston plot, showing the year of commissioning of some of these machines and the effective energy that you would get by compared to a cosmic ray, say, smashing into the atmosphere. And for many of these points, each one of these is a different type of accelerator complex. In many of them, as we went up in energy, we discovered new particles. And the end point of that, this highest point up here on this Livingston plot, is the Large Hadron Collider, which has been operating underneath the Swiss-French border outside the city of Geneva since about 2009, which has achieved the highest energies of collisions between particles, in this case protons, that we've ever achieved. And so just to give you a cartoon, the LHC is a circular collider that lives 100 meters underground underneath the French countryside. And in it, protons are circulated to very close to the speed of light. They're smashed into each other at a couple of very carefully instrumented points where there are detectors built by experimental collaborations that are just fancy modern versions of the cloud chamber, where they're looking for similar things to what Anderson and Nettermeyer were, evidence for new particles beyond the ones we've seen.
Nathaniel, what's the diameter of the...
The LHC ring is 27 kilometers. Okay, so if you walked around it, it would be a good 27-kilometer stroll. I've tried to walk on parts of it above ground. It's a little hard to figure out where it is at points. Sometimes you end up in French farmers' fields, but indeed, you're looking at a 27-kilometer ring. So the end point of that, indeed, the culmination of this program was the completion of what we now call the standard model of particle physics. This looks a lot like the diagram I started with, but it's slightly different. Remember, in 1932, it seemed like things were made of protons and neutrons. We subsequently discovered that those actually are made of more fundamental constituents, the quarks, the up quark and the down quark in different combinations. We had the electron and the muon, but then we've added this whole other host of particles. And the thing I want to draw your attention to is there's a replication, what's known as a family structure, where there's something like the electron, and then it has a somewhat heavier cousin, the muon. It turns out there's yet another cousin called the tau. And that structure is also reproduced for the up quark and the down quark. They have heavier cousins. Then there's a whole host of these peculiar ghastly particles known as neutrinos, which we also discovered first indirectly, then directly, which interact very weakly with everything else. In the center of this diagram are the force carriers, the photon, which as we discussed, that mediates electromagnetism between charged particles. There's what's known as the W and the Z bosons. These are the carriers of the weak nuclear force, which is responsible for nuclear decay. And then there's the gluon. This is the strong force. It's the thing that glues quarks together to make protons and neutrons. And at the center of all is something that was discovered at the LHC in 2012, which is the Higgs boson. So you've probably heard a fair bit about the Higgs boson. Its discovery was one of the greatest scientific discoveries of the 21st century. To give you some context for tonight's talk, I want to tell you a little bit, at least, why I think the Higgs is so important. And to give you a sense of why the Higgs is so important, why it's at the center of this diagram, I just want to tell you a story about all of these different particles, which all have very different masses and different interactions with each other. But it turns out if you write down all these particles and their interactions and you stare at them long enough, you notice something very surprising. You can make certain combinations of the photon and the W and the Z, the carriers of the weak force, and you would find that these combinations, they couple in the same way to all of these different particles, which is very unusual. These particles all have different masses. They seem to mediate very different forces. But if you look at them from a certain perspective, they all couple in the same way. That's evidence for what we call a unification of the forces, what's known as the electroweak interactions, that actually tells us there's some sort of symmetry that relates these different forces into some unified picture. Now, unification is a great thing for a theorist like me. In fact, if you made this observation and you take it to a high-energy theorist and you say, I've observed that the electromagnetism and the weak interactions, they actually respect a certain unification, a certain symmetry. An excited theorist will go away and say, well, that's great. Symmetry's unification is very constraining. In fact, I can tell you a fundamental theory that has that property. It allows me to predict the masses of all the particles. Okay? So the theorist would go and would work carefully, come back to their office with a piece of paper, and triumphantly say, here's my prediction, consistent with your observation of these unified interactions. My prediction is that all of the particles are massless. Okay, I can't wait to go to Stockholm. I've made a beautiful prediction. Of course, then you take this prediction to a hard-working experimentalist who goes out and measures the masses of all these particles, and they come back with something that looks like this. Okay, these particles all have very different masses. They're the light particles, things that we're made of. The heavier cousins have much higher masses. These neutrinos, which are almost massless. Some of the force carriers, which are massless, and some which are very massive. And so, of course, as a theorist, you're incredibly puzzled. There's a tension. There's a tension between this unification of forces, and this interactions being the same, and the masses being very different. And these things don't live together in the same theory in any nice way. And so there's a tension about what the theory is actually doing. So that tension was resolved by Peter Higgs and others by recognizing that it's possible to have a theory that has a unity of interactions, where in the underlying theory, the interactions are indeed all the same, but actually in the lowest energy state of the theory, what we call the vacuum, the masses turn out to be different. And the way that happens is the following picture. In fact, I even have not just the picture, but even a little physical model here that a friend of mine, his son 3D printed for me. We'll call this the wine bottle potential since we're in Santa Barbara. Okay, looks like the bottom of the wine bottle. Here's the punt, right? Depending if you're a red wine fan or white wine fan, you can take your pick. It's probably a Pinot bottle. The idea is that this is a potential, just like a ball on a hill feels a gravitational potential that it can minimize by rolling to the bottom of the hill. But this is not in the physical space of a ball. This is actually in the space of the Higgs field itself. So the Higgs field sees this potential. And so to minimize the energy in the universe, it wants to roll off of the top to some non-zero value at the bottom of the wine bottle. And what that means when the universe rolls down to occupy this lowest energy state, that means this Higgs field everywhere in space takes on some non-zero value. Okay, it's a little bit from the perspective of all the other particles in the universe, like filling up the universe with molasses. Okay, if the Higgs were sitting here at 0, and it's 0 everywhere in the universe, everything would fly freely through space. But once it slides down to the lowest energy configuration, is non-zero everywhere, all the particles that interact with the Higgs, they see this non-zero value, this molasses, and it slows them down. And the particles that interact the most with the Higgs, as they see this molasses, they slow down the most. They effectively have the largest mass. And the particles that interact with the Higgs the least slow down a little bit, and they have a very small mass. And so it's this that allows us to unlock this tension between the interactions, which seem to be unified in the theory, and the masses, which are very different. It's because the theory indeed is unified, but in the lowest energy state of the theory, different particles interact in different ways with this Higgs, and they effectively acquire different masses. So this allowed us to resolve the tension, and of course it came with a beautiful prediction. The beautiful prediction was if you excited the Higgs field around this minimum energy configuration, that would be a particle. That particle is the Higgs boson. And you have a wonderful prediction that the Higgs boson should couple to all the particles in the Standard Model proportional to their mass. And that tells you how you should look for it. So after decades of searching, of course, and successive experiments, indeed, the Higgs boson was discovered at the Large Hadron Collider in 2012. And I like showing this clip from the New York Times by Dennis Overby because it captures, the hyperbole, the incredible hyperbole that well justified of the Higgs. Physicists find elusive particles seen as key to universe. This was a big moment in my career. I was early in my life as a particle theorist, and I sort of, decided to spend the rest of my life studying the properties of the Higgs that we discovered at the LHC. Okay.
Let's see if there's questions.
Yeah. So the question is, I have a question for you. So are we done? Right? We have a list not just of all these particles that we've discovered by going to higher and higher energies, but we also have a hypothesis for how they interact with each other, and a way even to resolve a puzzle about their interactions and their masses. And so at this point, you might say, okay, maybe we get to go home. Of course, since I'm not quite through my talk yet, the answer is no, indeed, and this has been a remarkable, history of particle physics, but actually we're just getting started. So what does that mean? When my kids ask me, I've got a 5-year-old and an 8-year-old, and when they ask me, Daddy, what do you do at work? Some days I'm like, I sit in meetings, but other days I say, well, I get to contemplate the mysteries of the universe. And that actually is what the job feels like. It's an amazing job. There are lots of questions that we have with this picture that we know about, along with other experimental evidence that we've accumulated across, length scales from quarks to the cosmos, that we have lots of other questions. All right. Here's just some of them. Each one of these would be a KITP chalk talk in its own right. And because I just get one chalk talk, I'm going to have to restrict myself just to these first two. But I'd be delighted to chat with any of you afterwards or even on a different day about any of these other questions. But I want to focus right now on these first two. What is the question of the origin of mass? Well, I know you're probably sitting there wondering, didn't I just tell you what the origin of mass is? Higgs, it gets this molasses value, things become heavy. Indeed, this seems to be the case for all the experimental data that we have so far. So I told you, right, things get mass from the Higgs proportional to how strongly they couple. And so as we make measurements of how strongly these particles couple to the Higgs, you can plot them. You can say, okay, what's the mass of the particle? And how strongly does it couple to the Higgs? And if it's this prediction we have in the standard model, they should all fall on a line. And indeed, these measurements, the error bars are so small you can't see them. These are the measurements we've made of the very heaviest particles in the standard model, and they all fall along this line. So from one perspective, you say, well, we know the origin of mass. We know these things are getting their mass from their coupling to the Higgs boson. But there's actually, and you see lots of particles on here. These are mostly the very heaviest things. You can actually see the muon down here. We're learning about the muon in real time now at the LHC. But there's a very heavy particle that's not on this plot. Does anyone want to speculate as to the very heavy particle that's not shown on this line? It is shown, I'll give you a hint, it is shown in this table down in the bottom right corner. The Higgs itself. So the Higgs is not on this plot. But by hypothesis, the Higgs should also be on this plot. This is our current state of knowledge of the Higgs and how it couples to itself, which should give you the sense that we have absolutely no idea. This is actually a sign of a much deeper and more profound ignorance. So I've told you this beautiful story about the wine bottle potential, and that we know because the Higgs wants to settle down to the lowest energy configuration, it gives everyone mass, everyone space. And indeed, in the standard model, this is a very precise picture. Because once you've measured the mass of the Higgs, and once by measuring masses of other particles, you know where the bottom of the wine bottle is, what its value is, you're actually able to predict the rest of the shape uniquely. You know exactly what the shape is. In other words, if you think this is just a function of some variable h, you measure this, which is the h squared piece, that's the mass of the Higgs, and once you've measured this in the standard model, you know all of the other higher terms. In other words, you know the rest of this shape. Okay? So in the standard model, we have a very sharp prediction for this. And now you can ask yourself the question, what's our state of experimental knowledge? The way you would test this is you would say, well, this, we have a prediction for it. It's proportional to 3 Higgses, and so you would measure how often does 1 Higgs turn into 2 Higgses, and that would tell you what the value of this number is. So we try to do this at the LHC, but it's incredibly hard. The Higgs is very heavy. There's lots of other things that look like this, and it just turns out to be finding a needle in a haystack. And so to give you a sense of the state of experimental ignorance, I just want you to follow, you can either follow the slice here, or you can just imagine following just this edge here on this cutout. That's this line here. That's what the standard model predicts. And this band, this fuzzy band, this is the state of possibilities that are consistent with all the data we have. And to give you a sense of how radical that range of possibilities is, this shape, or this shape, are perfectly consistent with all known data. Okay, obviously, these things look nothing like this. In other words, the reason why the Higgs gives us this molasses, gives everything mass, we have absolutely no idea. Okay, no idea at all. And unfortunately, we're not going to be able to figure it out at the LHC. The collider is just not strong enough to do it. Now, this isn't just a question about the shape of wine bottles, although I know I certainly, and probably a lot of us here, are very interested in the shape of wine bottles. It's not just a question about the shape of wine bottles. It actually has something to say about the birth of the universe and the death of the universe. Knowing the shape at the birth of the universe, I'll give you a very quick version of the story. We know early in the universe was very hot. And something very interesting happens if you take a Higgs potential and you heat it up. It actually turns out that as you go to high temperatures, this little punt in the middle goes away, and it looks more like a bowl. Or in other words, if you cool down the universe from the beginning, it goes from a bowl to this wine bottle shape. And what that means is in the early universe, the Higgs is here at 0. There's no molasses, nothing has mass. As you cool the universe down, that no longer is the minimum energy configuration, and eventually the Higgs does what it does. But there's an interesting question about how this happens. Now, one of two things can happen. Either this happens very slowly and gradually, and the Higgs basically rolls from the top, from the middle of this bowl, out to the edges, very gradually. Particles gradually get mass, and we end up with the universe that we see. But there's another possibility, which happens very frequently, which is that the Higgs is sort of stuck in the middle for a long time until this bump actually gets quite large. And then quantum mechanically, it jumps from the middle down to the low energy part. These are two ways of ending up at the same point in the modern era, but they look very different in the early universe. In particular, if it makes this jump, what happens is something very remarkable. It's actually a lot like when you put a pot of water on to boil. It starts off as water, you're heating it up, and eventually you start making bubbles of water vapor, of water in the gas phase, inside the liquid. And those bubbles grow and they start to collide with each other. And eventually, of course, those bubbles are more and more, and all the water has boiled away. That's actually what would happen in this sort of second scenario where the Higgs jumps, is in the early universe, it would all be filled with everything being massless. And suddenly bubbles would appear, where inside the bubble, all the particles had mass. And it would be energetically favorable for these bubbles to expand. And eventually, they would fill the universe. And they would fill the universe with the particles as we know them. But this would leave behind a very interesting imprint. The collisions of all these bubbles would make ripples in space-time, which are gravity waves. And we're now in the era that we can begin to discover those gravity waves. So this is a really interesting experimental question. How the universe started has other signatures. It tells us really something very interesting about how we came to be. And we can actually go test it in gravitational wave observatories. But to know which version of the story played out, we need to know what the Higgs potential looks like, because that determines whether it was a smooth transition or a big jump. Might sound hyperbolic, but the shape of the Higgs potential also tells us about the death of the universe. Okay. Now, the good news is we think this happens many, many, many years longer than the age of the universe. Okay, so I don't think any of us will be around to see it. But the thinking is that actually if you take the Higgs potential and you study it at shorter and shorter distances using quantum mechanics, you actually learn that the picture I told you about, this nice wine bottle, this is a sort of a local little picture down here. And actually, as you zoom way out, it does something very unusual. The potential actually flops over. All right, so this is like if you took a wine bottle and from the top of the wine bottle, you peeled it all the way down. Okay. And what that means is there's actually a possibility, so we're living here, there's a possibility, quantum mechanically, that our universe tunnels out of this over this area where we don't even know how low the potential is. And this is a very rare process, so it takes much longer than the age of the universe. But eventually, if it can happen, it will. And then the universe will fill with something else. Okay? And it won't look anything like the universe we live in. So we actually think that the universe we live in is not a stable universe, but in fact, eventually will turn into something different. The question is, how stable or unstable is it? And exactly how stable or unstable it is depends, again, on the properties of the Higgs. So making these measurements are essential to figure that out. Okay. I want to briefly talk about the second question that we have time for tonight, which is the nature of dark matter. This is something I gather you may have heard from other Chalk Talks or other events at KITP. But there's another remarkable fact that, in fact, we talked about the story of the Standard Model, but it turns out most of the matter in the universe is not Standard Model stuff at all. This story began decades ago, making observations by Vera Rubin and others of the motions of luminous matter in other galaxies, where the normal theory of gravity plus the ordinary matter we saw would tell you that if you see some luminous matter that's spinning around and it's responsible for all the gravity in the galaxy, that there should be a rate for the motion of the spirals that's just predicted by Newtonian mechanics. But instead, what you see is something different. The rate, I don't know if you can see, the rate of the spirals is much faster as you go further out. And that tells you there's more gravitating matter further out that is not emitting light. So it's a sign that most of the matter in the galaxies is something different. Since then, we've accumulated a host of other evidence that, in fact, this is true. So it's not just galaxies, but all sorts of measurements that we make. And in fact, it tells us a very remarkable picture. Everything we're made of is about 5% of the universe. About 27% of the universe is also matter, but it's something that we don't know what it is, and it doesn't interact with light. Then actually, most of the universe, most of the energy budget of the universe is something called dark energy. That's a whole other mystery. Again, that's about 10 more Chalk Talks. So I'm not going to focus on dark energy, but ask me afterwards. But most of the matter in the universe is not stuff that we're made of. The problem is there are lots of things that could be dark matter. So this is just a plot of all the possible different masses and energy scales that dark matter could be, lots of different fabulous names for what dark matter could be. And so, of course, if you're in the business of trying to figure out what dark matter is, it's a very challenging game to play. But we have one thing to go on, which is there's, within a factor of 5, the same amount of dark matter and normal matter. And so we think maybe dark matter talks to us with some interaction beyond that of gravity. And if that's the case, then you can build very careful experiments to look for dark matter scattering off of normal stuff. This is a lot like those early cosmic ray experiments, except now cosmic rays are bad. These cosmic rays can scatter off your experiment and give you a signal. So if you want to find dark matter, you have to bury them deep, deep underground. And so indeed, this program has been going on now for decades, in fact, culminating with a beautiful experiment called the LG experiment, which is partially run by physicists here at UCSB, which is about a mile underground in Leeds, South Dakota, looking for very occasionally dark matter passing through the Earth and scattering off the detector. But the problem is there's still lots of candidates. There's a large range of things. And so the question you probably have is, Professor Craig, if you had to wake up one morning and bet everything on what dark matter was, what would you bet that it is? And the answer I would tell you is, I would bet that dark matter is a thing where if it talks to us with exactly the right strength, that the way it interacts with the standard model in the early universe gives us the observed amount of dark matter. In other words, if I tell you what the particle is and how it talks to everything else, that also allows you to predict in the early universe the amount of dark matter we observe. That's a prediction that I would say is probably true. And the problem is, if you ask what is the simplest thing that does that, the good news is it's within the mass range that we can probe by experiments. The bad news is it lives in a place where it interacts with the standard model, where there's a much more often thing that happens. It looks exactly the same, which is that neutrinos, this other ghostly part of the standard model, neutrinos interact with the same way, but much more frequently. So we're in the process of building these experiments, these beautiful experiments like LZ, which currently are probing these interaction strengths to high precision. We're going to improve by orders of magnitude in the future, but the thing where I think dark matter lives, we're actually never going to be able to get to with this method, because the neutrinos that are mimicking the signal of dark matter will be blinding us to it. So the question is, how can we move forward? Right? We have these deep questions about the origin of mass, the beginning and the end of the universe, what everything is made of, but it seems like an experimentally somewhat of a desperate situation. And so the first thing you might say is, well, we have the LHC, so that's a 27-kilometer ring, and that's smashing protons together at about 14,000 times the energy of the rest mass of a proton itself. It actually turns out when you smash protons together, you don't convert all of their energy into new stuff. Protons are made of other things. It's a bit like smashing two jumbo jets together. Most of what happens is things go all over the place. But a fraction of that energy can be converted into making new particles. It's about a tenth of the energy of the collisions. So the first thing you'd say is, well, maybe we just build bigger colliders and go to higher energies. So you increase by an order of magnitude the energy scales you probe to start making progress on these questions about the Higgs and about dark matter. You need a ring that's about 100 kilometers in circumference. And you can do that, but we think that to build that and to make a collider in it is something we could do by about 2075. So that's a challenge, because I don't think I'm going to be doing physics in 2075. If I can convince my daughter and my son to get into particle physics, maybe they'll be doing it. But that's a long time to wait to ask these questions. And the thing that's happened in the last couple of years is the idea that we can actually get to the same answers without building a 100-kilometer ring. In fact, building something even smaller than the LHC, but by switching from colliding stuff we're made of to colliding muons. Now, we didn't come up with the idea of colliding muons in the last few years. This idea has been around since the 1960s, but it turns out it's a very hard idea, mostly because muons, as we discussed, they're unstable. You can collect some muons and they decay. And so how you actually collect bunches of muons and turn them into beams that you can collide into each other turns out to be a really amazing technical question that people have grappled with for decades. Now, I told you this was an underdog story, so here's where the underdog part comes in. We got to the point where we figured we might know how to do this, and indeed, the US government funded what was known as the Muon accelerator program to really put this into action. They started in about 2010, and in 2014, they shut it down. Not because it had failed at anything or it seemed too hard, but basically because up until this point, it was a question of what's a cool accelerator we can build that's different from the other ones we built. And there didn't seem to be enough reason to build it. But something else happened around this time, which is we discovered the Higgs. And by discovering the Higgs and learning more about dark matter, we got a much better understanding, actually, about what the fundamental questions were we might want to ask of nature. And as soon as we got there, then we sort of understood that actually a muon collider might be the fastest way to shed light on these questions. And that gave rise to, after a bit of a gap, to a period of excitement and energy. And where I enter this story is I got together in 2020 with my students and postdocs and a couple of friends, and we basically understood muon collider is a very interesting idea. No one seems to want to build one, but maybe we haven't actually understood why you would want to build a muon collider in the first place. And so we sat down during the pandemic, so there was a lot of meetings over Zoom, and we figured out why muon colliders were very exciting. And we wrote a paper about it. In fact, it wasn't just a paper. There was an article about this in Scientific American last year where the author, Dan Garisto, I think correctly identified the thing that we wrote as a manifesto. We basically tried to figure out why this is something exciting to build, and then we tried to communicate it to other physicists in the community. And when we started doing this, people told me there's no second acts in American particle physics. Now that the muon accelerator program is canceled, you will never bring it back. But what's been remarkable is that we seem to have brought it back. And just to give you a sense of how it could come back, just to briefly connect it back to these two questions that we've been dealing with, the origin of mass, the miracle of muon collider, is you can very easily convert all the energy in the muons to making new particles. And so it's very easy to test the properties of the Higgs that we need to test to figure out what's the shape of this wine model. So again, we can go from this state of grave uncertainty here to a state of immense clarity with the precision that we expect from a muon collider. And it seems pretty clear, if you get this precision, we'll know if this is what we've got or if we've got something else. It's the precision, in fact, that with that precision, we'll be able to really know, have confidence in this answer to the question whether the universe began with these collisions of bubbles and when, if ever, the universe is going to end by tunneling somewhere else. As for the question of dark matter, we said one way we look for dark matter is by having the dark matter in the universe scatter off of ordinary stuff. But you can also turn that on its side and say, well, if I smash two standard model particles together, maybe I can make dark matter. This is very hard to look for at colliders, but again, a muon collider turns out to be the perfect place to do it. And by making very careful measurements, we can actually get to these simplest possible explanations for dark matter with these very weak interactions with the standard model. It turns out in this long list of wonderful questions we get to contemplate, the ones I've highlighted in blue, you can also make tremendous progress on them with the sort of opportunities you have at a muon collider. And again, I'm happy to talk to you about these questions offline, but each one of them is sort of a miracle in its own right. So this is not going to be easy. To make a muon collider, first thing you have to do is make muons. So to do that, we smash protons into a target, and the things that we make then decay into muons, a lot like cosmic rays in the atmosphere. Then we have to collect those muons into bunches and get them all moving in the same direction, and we have to do it before they decay, right, which is 2.2 microseconds. This is something we've never done before, and so we need new technologies to make these accelerators, but we know how to do it. Once we do it, we also get them moving around in rings, but the problem is some of the muons that move in these rings, before you collide them, they decay, and you have to deal with those decay products bouncing around your ring too. For a long time, people thought you can't possibly look for new particles with all of these things happening in the accelerator complex, but actually everything we've learned from the LHC has taught us how to handle that problem too. So it turned out that decades ago, people said there were 12 miracles that had to happen in order for a muon collider to be realistic. And we're at the stage, I don't want to go through this in detail, but just to convince you, those 12 miracles are now interesting technical challenges. We've solved about half of them, and the other half we actually know how to solve. And so this is something that we can build, not tomorrow, but the expectations we can build it about 2045, which is, I think from my perspective, in terms of asking and answering these questions, a lot closer than the 2070s. So we took these ideas, as Mark alluded to at the beginning, the way things work in the US is first physicists get together and decide what they'd like to do. And remarkably, people came together, and with the input of us and others, they decided that what we wanted to do was build a muon collider. And not just build a muon collider, but build a muon collider in the US, which is an interesting challenge because to build a muon collider in the US, it has to fit on the footprint of a US national laboratory. And it just so happens that the muon collider that can answer all these questions fits on the footprint of the Fermilab National Accelerator Laboratory, which is outside of Chicago. But of course, the way this works in the US is we all get together, decide what we want to do, and then we pass it to another more responsible panel who says, well, this is what you can afford to do. And usually that's the point where most ambitious ideas die. But this actually went to that panel. That panel convened in this last year and came out with its report recently. And that panel also agreed that this was a vision that was worth pursuing. And so this recommendation now goes to the US government, not to build the collider starting tomorrow, but to undertake the last steps of research and development that will get us to this point. So it's an underdog story because we have these deep questions. It wasn't clear how we were possibly going to make progress on them. This one idea everyone thought had died and gone away. It's now come back, and now it looks like it may well be the actual way that we make progress on these questions. But I don't pretend this is easy. Of course, this is incredibly hard. So the question is, why do something in fundamental science that is incredibly hard and, of course, incredibly expensive? And to answer that question, I hope you'll forgive me if I borrow a little bit from John F. Kennedy. As I hope I've conveyed to you in this talk tonight, we set sail on this new sea of building these colliders because there's new knowledge to be gained across the frontiers of particle physics. We've talked about the origin of mass and dark matter, but of course there are many more. So we choose to collide muons. We choose to collide muons in the coming decades, not because it is easy, but because it is hard, because that goal will serve to organize and measure the best of our energies and skills, because that challenge is one that we are willing to accept, one we are unwilling to postpone, and one that we intend to win. So this is our muon shot. Thanks very much for listening to me. If you'd like to learn more, there's a website for the newly formed US collaboration where you can learn a lot more, and I'm happy, of course, to talk to you afterwards as well.
Thank you, Nathaniel. I'm sure we have yes.
Obviously, you got this pun going about moonshots and muon shots. Which is more expensive?
The moon, going to the moon, absolutely. The cost of a muon collider is about the same as the James Webb Space Telescope. The cost of a muon collider is about the same as the James Webb Space Telescope. So James Webb came out a little bit above $6 billion, I think, depending on how you do the costing. The costing for muon collider is $7 to $12 billion in 2020 dollars. It's about a third the cost of that 100-kilometer ring.
So we know how they accelerate at the hadron with magnets, electricity, particles, positive, negative charges. How do you accelerate something with no charge?
Well, the muons have charge. The muons
How
are.
do you accelerate something with such a tiny little charge?
Oh, well,
that
so.
they didn't even notice?
Oh, good. No, so good. The charge is actually the same as the electron, and it's 200 times heavier. So the reason we didn't know about it for a long time, yes, the neutrinos are hard. They have no charge, and they're an interesting complication of the problem. But the muon, it has the same charge as the electron. It's 200 times heavier. That makes it about, it's 10 times lighter than the proton. And that's actually sort of a perfect sweet spot for the following reason. You might ask the question, we said protons are hard because you smash them together, you lose a lot of the energies just in the protons breaking up. Why can't we just smash electrons together at very high energies? That seems like smashing muons together. The answer is, of course, if you take a charged particle and you try to accelerate it, it loses energy by radiating. And it turns out the power loss to that radiation goes like 4 powers of the mass. Okay, 1 over 4 powers of the mass. So it turns out that the highest energy circular, in fact, before we built the LHC, we actually collided electrons and positrons in the same ring. And we got to energies that were about 20 times less than the collision energies of the LHC. And that was the speed limit. Any higher, and you were taking all of the power in Europe to basically drive those electrons and positrons around. So now, if instead you put in that ring something that's 200 times heavier, then you can get to much higher energies. So that's why muons are sort of in this perfect place in between. Yeah.
Yes.
So the U.S. famously failed to support the superconducting super collider. What kind of argument would you make and why this would be one they should?
Absolutely. So I'm so happy you asked that. My wife actually, so my wife's from Dallas. She actually made me take out, so I've actually spent a lot of time in Waxahachie, which is where the superconducting super collider was under construction. On holidays when I go visit my in-laws, they let me escape for an afternoon, and they all say, Nathaniel's off walking in the fields. And just because precisely the specter of the SSC looms over any ambitious particle physics in the U.S. And I think there's a beautiful book about this called Tunnel Visions, which was about the politics of the rise and fall of the SSC. And there are a couple of very central lessons. A lot of it had to do with, of course, the situation of the time. Another main lesson was don't try to build a collider in a green site. In other words, don't go build an accelerator complex someplace where the physicists aren't living and the facilities aren't present. And so this is actually why, for decades, people thought, well, we can't build another collider in the US because we can't fit one that we would like onto the footprint of a US national lab. And so that's, in some sense, why the Muon collider is transformative for the US, is that we could do it at an existing campus. And I think if you ask about the reasons for the failure of the SSC, the overarching one, the one that I think people think would have reversed the outcome had it been different, is the decision to build it in Texas where no national laboratory existed, as opposed to in Illinois where Fermilab already existed. So the fact that we can do it there is important. Another thing that's very important is right now, actually, Fermilab is committed to about a 20-year program of neutrino physics. And we don't know what to do there after that. But it actually turns out that everything you do to build a muon collider is perfectly interleaved with everything that we're doing with the neutrino physics program. So actually about half the battle in terms of how you actually get these muons will have already been fought through the existing physics program. And so these are the reasons for optimism. I think the other thing I think that gives me hope is that, at the time, building the superconducting supercollider was what you might call an example of a divergent physics goal. It was a particular community of people who had particular questions, and they were asking for many more resources than anyone else to do them. Right now, looking towards the Muon collider, it's not it's of the same scale as large experiments in many fields, but also because of many aspects of Muon collider physics, which I'd be happy to talk about later, it's actually a convergent physics path. There's lots of things. I've given you 2 stories about dark matter and the Higgs. We actually stand to learn an immense amount about, for example, neutrinos, other things that are relevant to astrophysics and cosmology. And so I think also it's just a convergent path for physicists, and that also gives me a lot of hope. But I'm really glad you asked about the SSC, because it's,
Great.
With the recent discovery of the superconducting magnets, supposedly higher temperature, above 20 Kelvin, with no insulation between the layers, will you be able to use, and the lack of quantum fluctuations that they can,
indeed, this is a wonderful observation. Any developments in high temperature superconducting technology are natural wins for a muon collider. So the magnets that we would need to get the muon collider that we want are somewhat higher field than the ones we currently use for the LHC, but they're within reach. Anything that brings down the cost or brings down the power needs of those magnets indeed makes it more achievable. So that's another thing you can ask, why do we even do this in the first place? And the answer is that these science needs help to drive technology developments. And so indeed, new developments in high TC superconductors and high field magnets should help a great deal.
you're following those?
Yes, very much so.
Great.
Yeah.
Thank you.
Yes.
One of your slides along the bottom, you had a nuclear cross-section, and I think I saw 10 to the minus 42nd meter or something like that.
Good, yeah. This is the dark matter nucleon cross-section. So how often, what's the, in some sense, what's the probability?
I was wondering if it's Planck, what's the Planck area, Planck length? I mean, it's smaller than that. Or
Good,
bigger than
it's
that,
much,
isn't it?
let's see, I'm here.
There it is.
Good. So I put down here is very small. So the units, a famous unit that was developed, during the development of atomic weapons is the barn, which is the size. So cross section, of course, is just an area. Uranium nucleus is about 10 to the minus 24 centimeters squared, and so of course that was easy to hit. So it was like hitting the side of a barn. So indeed, it's remarkable that it's extraordinary, right? If you think about it, the effective sizes, right? This tells you how weakly dark matter, we think, interacts with nuclei, is the effective sizes of the interaction are 20 orders of magnitude, right? 1 with 20 zeros smaller than the size of the uranium nucleus. But of course, the Planck length, or a Planck area, is much, much smaller still. So we're not remotely, much smaller, yes, much smaller. Orders and orders of magnitude. Yeah. No, that's quite, I mean, indeed, it's remarkable, orders of magnitude. Anytime you see 20 orders of magnitude, usually interesting things happen. But we're not in the regime of quantum gravitational effects.
Yes, thank you.
Did you consider a linear electron-electron collider?
Very good. Indeed. So actually, if you go up in my office at KITP, there's a name tag on my desk that my wife got for me about a decade ago. It says Nathaniel Craig Collider Salesman. And the reason for that is that in some sense, colliders in general, they've been the past and the present and the future of the field. And so I've always felt that it's important to understand and make the case for these colliders. And so something I have spent some time thinking about is a proposal for a linear collider, which is now called the International Linear Collider, the ILC, which as of the last decade would be cited if it's constructed in Japan. The ILC is a beautiful idea. I told you that the Muon collider sort of came back because we discovered the Higgs and we understood what questions we started to care about. The ILC, in some sense, was designed in an era where we thought the questions would be different. And it turns out it's just not well suited. It doesn't go up to high enough energies. And it can't actually get the statistics that you need. The real challenge of a linear accelerator, although it doesn't have the radiation energy losses, because you're not accelerating in a circle, instead of circulating beams and colliding them many times, every time you want a collision, you have to fire a new bunch. And it turns out that it has a rep rate that limits you. So the ILC is a beautiful idea, but it's sort of been in purgatory for about a decade since the discovery of the Higgs, because we no longer think that that's the right machine for the physics questions that we're confronting. But it's an amazing question. Thanks.
Sure.
Yes,
if real estate legal problems exist, why not space or the moon? And as an advantage, you get a free vacuum system.
Indeed, yeah. You wouldn't nearly have to worry about pumping down.
And also, you put an umbrella or shade up and you get great cooling for magnets.
No, these are great questions. I mean, part of the problem, so space is hard. The problem is, we're good at putting satellites into space, things that are compact, objects, extended things. So it turns out there's too many things going on in space for you to shoot the beams in free space itself, and for you to, be able to, turn them on the path that you need to build their energy and have them collide. The moon is interesting, but, getting anything to the moon is hard, and getting tons and tons of magnets to the moon and operating them is harder still. So, absolutely, you could ask the question of what does the ultimate collider look like? And the answer is maybe it looks like something on the moon. But it's remarkable to me that to make this huge leap in our understanding of physics at short distances, we don't need to build something on the moon. We don't need to build a 100-kilometer ring. We just need to collide this very remarkable particle actually in a very small accelerator. So indeed, the KITP chalk talk in 100 years probably will be about accelerators on the moon. But I think it's remarkable that we can make a lot of progress with accelerators at Fermilab. It's a great idea.
Yes.
So the muon weighs 200 times the electron. There's another one though, right? Tau?
Tau, yeah.
And it's heavier?
The tau's heavier, yeah.
How about we use it?
How about use tau? Good. Couple of things. It's harder to make taus, and taus decay a lot faster. And so the real issue is, so the part of the lifetime of these particles, the heavier you are, the faster you decay. And so a muon is 2.2 microseconds is not a long time, but you actually can take advantage of the special relativity effect of time dilation. And so basically, if you get the muons moving fast enough in the lab frame, from your perspective in the lab, they live a lot longer. So it turns out that 2.2 microseconds is enough to make it work and to collide. But taus basically decay too quickly to get bunches. Exactly. So you can't build the luminosity. Yeah, no, it's a very interesting idea, but they're just too unstable.
Great questions. I think if you have more, can come up afterwards. So let's thank Nathaniel again.
Thank you so much.